Welcome to ECE 501B. I'm entitling this session Vector Space, Sums and Direct Sums. And really we're talking about now how do you combine subspaces, how do you add them, how do you sum them, and there's a special kind of way to combine those, summing those, and that's going to be called a direct sum, and we'll get more into that at the near the end of this session. Before we start though, here are our goals. I want to review subspaces. I want to then define these two concepts of vector space sum and vector space direct sum. We'll look at some examples of direct sums and maybe some examples of subspaces that don't combine to form a direct sum. And we'll present propositions 1.8 and 1.9, which provide us with another way of establishing insight into these direct sums. Let's review a little bit about subspaces before we start building up with subspaces or putting subspaces together. We learned how to start with a space and we broke it apart or separated it up into subspaces. Let's just talk a little bit more about subspaces before we get started building them back up. If we have a subspace U of a vector space V, then that set U or subset, it must be a subset of V, it must come from V, and U must satisfy all the properties of a vector space. If U is a subset of V, then U actually inherits all of the properties of V. And to verify that U is a subspace of V, we only need to show or check three properties. One is that the zero element is contained in this subset, U, or we have the additive identity present. The subset is closed under addition, which means if we start with a vector U and a vector V, both in this subset of vectors, U, then if we sum those two, it remains in the subspace or the subset U. And this subset needs to be closed under scalar multiplication. If we take an element from the field F, which could, most of the time we're talking about that field being the real numbers or the complex numbers, R or C. And if we take a vector from our subset of vectors in U, if we scale that vector by this scalar A with our scalar multiplication, that result needs to remain in the subset U. If those three properties are satisfied, then U, this subset of elements in V, is indeed a subspace. Just to go back and look at some typical subspaces, subspaces of R2, it could be simply the origin, the smallest subset. It could be the largest subspace, which is R2 itself. So we always have those two subspaces in a vector space. We have the smallest subspace, which is the zero element, and we have the space itself, in this case R2. The other collection of subspaces of R2 are all the lines through the origin. Pictorially, then, we have these three examples. We could have the x-axis, that forms a subspace in R2. We could have the y-axis, that forms a subspace in R2, and note that those two both contain the origin. We could also have this 45-degree line going through the origin, which has equal x component and equal y component. That also forms a subspace in the vector space R2. What are some examples that are not subspaces? Well, we have a line that's not going through the origin. That's not a subspace. We could have all of these points that are at integer separation values on, let's say, the x-axis or script z sub x. That particular subset of R2 is not closed under scalar multiplication, as we talked about in a previous lecture, and consequently that does not form a subspace in R2. Likewise, we could extend that concept of subspaces of the plane R2 into subspaces into the volume, or this three-dimensional space R3, and this is coming from a sentence that spans or goes across pages 13 and 14 of your textbook by Axler. It could be the smallest subspace, the origin. It could be the vector space itself, which is R3. It could be lines through the origin, or it could actually be planes through the origin. Any of those would form a subspace of R3. Before we get into sums and direct sums, let's just briefly remind ourselves that the union of subspaces are not really the same as the sum of subspaces. Let's take U to be, let's say, the x-axis in R2 in this plane, xy plane. Let's take V, the subspace V, which is the y-axis. Then the union of U and V, that only consists of the points on the x-axis and the points on the y-axis, nothing in between. There's nothing at 1, 1 in that particular union of subspaces, script U and script V. The point 1, 2 is not contained in the union of U and V. Contrast that with the sum of those two subspaces, and the sum does encompass the entire xy plane. That's trying to be indicated by the yellow shading or highlighting of the xy plane. What do we mean then by sums of subspaces? Suppose that we have a finite number of subspaces. Let's say we have m of those, Michigan of those, and they're subspaces of this vector space V. Then the sum of u sub 1, u sub 2, u sub n is defined. This is the definition. It's to be the set of all possible sums of elements of u1, u2, and u sub n. We can take any combination of vectors in u1, u2, um, and the sum of those vectors form this subspace of the sum of those m subspaces. Symbolically, or let's say the way that you might compute that is if you wanted to add u sub 1, u sub 2 up to u sub m, those m subspaces, then you take an element from all of those, or that you could take elements from all of those individually, and their sum then forms this combination or collection of elements that create the sum of that particular set of m subspaces. Let's look at some examples of that. Suppose that we now let this subspace U actually be a vector in R3 that's just the x component. We're allowing U1 to be any real number. Suppose we have another subspace V that is defined to be this line going through the origin that has equal x and y components also in R3, but it's such that V1 also is any real number. What does that actually represent then? If we now looked at the sum, I'll say the sum of U subspace and V subspace, I'm going to call that a new subspace S. U plus V, that's now going to be this combination of the sum in component-wise form of these two subspaces, meaning we have U1 plus V1 in the first element, we have V1 in the second element, and we don't have anything in the third element, making up our vectors in R3, such that we can make U1 anything we want in the real numbers, and V1 is anything we want in the reals. But that's equivalent or equal to x comma y comma anything in the xy plane in R sub 3, since now we can actually find x to be U1 plus V1, which is by selection of V1 and then U1, we can find any number we want to form x. Y is simply V1, which is also real, and so S is now simply the xy plane, lying within this three-dimensional vector space. Now that we know how to sum subspaces, we sum their individual components, we're actually going to be interested in situations where, or in cases, where when we sum those subspaces, we actually fill out or can completely fill the original vector space V. So we want the sum of U1, U2, and U sub m to be V. Now that's fairly common, but we also want to make this a little bit more particular or special, and so we want to create something that we will call the direct sum. So now the original vector space V is the direct sum, and this is how we are defining direct sum, of these M subspaces U1 through U sub m, which we will write as V is equal to U1 sum with a circle around it plus U sub 2, another sum with a circle around it. So all of our summations actually have this circle around it if, so V is equal to the combination or the sum of these M subspaces, and we're going to call that a direct sum if each element, each vector, each element of V can be written uniquely as a sum U1 plus U2 up to U sub m, where we're pulling these vectors out of each of the M subspaces that we started with. Meaning we can't find three different ways or two different ways of linearly combining vectors from U1 up to UM to find any arbitrary or generic element in the original vector space V. We have to be able to find unique combinations from each of those M subspaces. If that's the case, then we have this direct sum of subspaces forming our original vector space V. This maybe will be a little bit more clear if we look at some examples. The first one let's start with is the easiest one. Suppose that we now have subspace script U, and we'll just be playing with R3. And let's just let that subspace be the x-axis. Let's say that we now have another subspace Y, which I think you can anticipate what that's going to be. That's now just the y-axis. And let's then create another subspace W, which is the z-axis. Now I think it's pretty clear that the original vector space R3 is indeed, or can be written by combining unique vectors from u, y, and w to create any vector that we want in that three-dimensional space. We just need to scale the x vector, or the subspace on the x-axis, the subspace on the y-axis, and the subspace, any vector in the subspace on the z-axis, and we can find any element that we want in R3, or this three-dimensional space. Now, what you don't want to necessarily draw from that particular example is that these subspaces that create direct sums don't necessarily have to be orthogonal. And we'll learn more about orthogonality in subsequent lectures, but I think you already have a good feel for what that means. But let me just say that the subspaces do not have to be orthogonal to provide what we're calling this direct sum. To illustrate that, let's look at a second example. Suppose that U is now this 45-degree line going through the origin in the xy plane of this three-dimensional space. Suppose that y is the y-axis in three-dimensional space. And suppose w, if we want these to be completing or creating R3, we obviously now need to pick up at least the z-axis, and that's what w is doing. So that now V, which is the three-dimensional vector space, is u plus y plus w, and we can find unique combinations of vectors in u, y, and w that represent any vector in this three-dimensional space. Meaning for any, let's say, x contained in V, then we can find an x, which let's say has these three components, x sub 1, x sub 2, and x sub y, by the choice of unique vectors coming from these subspaces u, y, and w. Meaning, if we look at this, we have coming from the u subspace, we get u and u. Coming from the y subspace, we get a y into that second component. And from w, we get the third component. So that if somebody gives us an x, then we can find x1, or we can find unique elements in u, y, and w that will produce the x that we were given. We can do that by letting w equal x3. If somebody gives us x, they're giving us x sub 1, x sub 2, and x sub 3. Then we can simply set w equal to x sub 3, and that's going to be a vector from script w subspace. We can also let u be x1, and then the only really tricky part is to let y be x2 minus x1. And that's possible since if you look at what x2 is, that's u plus y, but we've already picked u by the choice, or since it needed to be set equal to x1, so this is now x1 plus y, and so y is now x2 minus x1. And that's another direct sum, and in this particular case, we didn't have orthogonality with respect to all of the subspaces. We had the xy line, we had the y line, and we had the z line, but u and y together basically give us the xy plane, and w gives us the z direction. Let's look at another direct sum. These subspaces could be larger than just one dimension in size. For example, suppose that u is not just one dimensional. Let's say that it actually spans this xy plane in R3. By that, I'm letting u be any real number and v is any real number. And w, in order to complete R3, let's just let that be the z-axis. And I hope it's clear that all of R3 is this direct sum of subspace u and w. So those are some examples of how we could actually create or illustrate this concept of direct sums, which is a way of building back up a complete vector space from separate subspaces. And those subspaces do not have to be one-dimensional subspaces. Let's now look at some propositions at the end of chapter 1 that really are, let's say, helpful in deciding if certain subspaces are combining in a direct sum manner to produce the entire vector space that we want them to create. So these propositions are helpful in deciding if a collection of subspaces is a direct sum. The first proposition really answers the following question. Can the zero element in your vector space V be represented uniquely by vectors, or let's say by vectors u1 element of u1, u2 as element of u2, on up to u sub m, an element of u sub m. Is it possible to only find one way of creating the zero element from all of these subspaces, u sub 1, capital U sub 1, u sub 2, up to u sub m? That's the first proposition, really, is what it's saying. If it's possible to find a unique combination, and actually that unique combination needs to be the zero vector in all of those, then we have a direct sum of our original subspace. Let's look now at proposition 1.8. Suppose u1, u sub 2, up to u sub m are all subspaces of V, then V is this direct sum of these M subspaces if and only if A, we can actually fill up all the vector space by summing u1 through u sub m, so we can generate all the vector space V. And the other point is the only way for vectors from each of these M subspaces to equal 0 is for all of these vectors to be the zero vector. For all the, let's say, u sub i's contained in capital U sub I. And this is a shorthand way of saying for all. Let's actually look at an example, and in particular, this is a negative example of a direct sum, meaning this particular combination or sum of subspaces is not going to be a direct sum of the original, let's say, three-dimensional space R3. Suppose U is now U1, 0, U sub 3, where U1 and U sub 3 are not the same, but they are any potential real value or real number, which means really that script U is the xz plane. Suppose Y is the subspace Y is the Y line, or the Y direction. It's really just the Y-axis, I should say. And let's say W is now, let me call that W sub 3, 0, W sub 3. This is a line in R3, and where is this line? Well, that line is now going through the xz plane. It's just at a 45-degree angle. The x component and the z component are equal. So this is a little bit different than U that we just created. U is the xz plane. W is just a line in that plane. So now what we want to do is we want to check, and I've already told you that this is a negative example, but we want to see if V, our original vector space, which is all of R3, is that a direct sum combination of these three subspaces, U, Y, and W. So if we look at this, we are really wanting to determine, based on proposition 1.8, can we find two different ways of creating the zero vector by the particular choice of vectors in u, y, and w. Meaning, if we look at this, we're literally pulling from these particular subspaces. So from the first one, we have two independent real numbers, u1 and u3, in the x direction and in the z direction. From y, we get the second component, and from w, we can now add in a w sub 3. And we want to know, first, can we find values? Ideally, we would want to only be able to find values for these u's, v's, and w's that were 0 in order for this to be a direct sum. If we can find different combinations of these u's, v's, and w's that produce the 0 vector, then u, y, and w will not be a direct sum of R3, a direct sum of subspaces. First of all, let's just make sure that u, y, and w do span all of R3. If they didn't do that, then there's no way that it could be a direct sum. We need it to at least be able to fill up all of R3. So if we start with any three-dimensional vector x, let's call that x sub 1, x sub 2, and x sub 3, then we can create that, or can we create that, from vectors in u, y, and w. And in fact, since the u's are independent, u sub 1 and u sub 3, we can actually find any value in the x component and the z component in that first vector. We can find the second component by any choice of v sub 2. So really, we don't even need to have or pick a non-zero w sub 3. We could simply just set w sub 3 equal to 0, and we will then end up with u1, v2, and u sub 3, and those are independent of each other, and so given any x in R3, we can combine or pull vectors from u, y, and w to generate that particular x. So indeed, we can find any x as a combination of elements from these three subspaces. Now, what we want to do is show, if this was to be a direct sum, we could only find one unique representation for the 0 element. But in this particular case, we can actually build this 0 vector from two different combinations of vectors, at least two different combinations. One of those, let's say, well, let's say this vector is the vector from y. The first one is some vector from u, and the last one is this vector from w. Suppose that we pick ones in w sub 3, which has to be in both locations. Now we need to form this 0 vector, and the vectors coming out of the subspace y only have non-zero entries in the second element. And if we remembered, this vector also had a 0 element, so we're forced to put a 0 right there. But in terms of vectors in U's subspace, we can now pick a minus 1 for u sub 1 and actually a minus 1 for u sub 3. And that vector then, when combined with this vector in w, produces the 0 vector. But we could also produce the 0 vector by simply pulling out the 0 vector from all of those three subspaces. So here's a vector from U, here's a vector from the subspace Y, and here's a vector from the subspace W. Now we have two different ways of creating or building the entire 3 space. Consequently, the 0 vector, can be written in more than one way, which means that 0, let's say, is not uniquely defined from U, Y, and W, and because of that, then U, Y, and W they do not form a direct sum of R3. Let's finish up by looking at proposition 1.9, which again is working with direct sums. Here, we are going to assume or suppose that U, these subspaces U and W, are given. Let's suppose U and W are subspaces of V. Then U and W form a direct sum representation of the vector space V if and only if we can find or we can create any vector in V by a sum of vectors coming from the subspace U and W, and if we've looked at the intersection of U with W, the only element in common with those two subspaces is actually the 0 element. What is proposition 1.9 saying? It's really saying that the two subspaces U and W need to fill up, or to fill all of the original vector space V. But in the process of doing that, their only subspace in common needs to be the origin or the 0 element. But their only subspace, which is really their intersection, that is shared between those two subspaces U and V, the common subspace is the origin. So if you can find the intersection of U and W, and it's the origin, and you can show that any vector in V can be represented or written as a sum of vectors from U and W, then you know that U and W form a direct sum of the subspace V, or I'm sorry, of the vector space V. That completes then our coverage of Chapter 1 material.